In continuance to my previous video lecture, in this class, I'll discuss the next few topics of relation. So in last class, I was discussing the matrix representation of a relation. So this problem I was discussing here, I see if I have ordered pair representation, I can write the matrix representation. If I have a matrix representation, I can write the ordered pair representation. So here this matrix has 3 rows and 4 columns. That means the first set will have 3 elements and the second set will have 4 elements. Okay, now suppose first set elements are A1, A2, A3 and second set elements are we are representing by B1, B2, B3 and B4. So wherever we have 1, that means that order, that particular pair we have to write. Otherwise, if it is 0, we need not write. So here this is what A1, B1. So A1, B1 I am going to write. This is A1, B2. So that is 0, no need to write. A1, B3 also no need to write. A1, B4, 1 is there. So I have to write A1, B4. Now in the second row, I have only second and third element. So I will be writing. So this is for A2 row. So A2, B2 and A2, B3. Now in the fourth row, I have a first and third element 1, second and fourth is 0. So I'll be writing A3, B1 and A3, B3 because first and third elements are there. So like see here we had a relation and ordered pair representation and we could write matrix representation from it. Now here in this example we have matrix, so we can write the ordered pair representation of the relation. Okay, now the next representation is digraph of a relation. So digraph is also called as directed graph. So when I talk about graph, it will be a collection of vertices and edges. So here what we have to do, see either matrix will be given to us or ordered pair representation of the relation will be given to us, and then we have to write the corresponding digraph of that. So basically what we have to do, we are saying if A is a finite set and R be a relation on A, means if R is a relation on set A, that means R should be a subset of A cross A. Now what we are doing, we have to draw the circle. Circle here represent the vertices of the graph, and and label the circles with the corresponding element of A. Means suppose A has 4 elements. So how many nodes I have to draw for the graph? I have to draw 4 nodes. So if the elements are 1, 2, 3, 4, so each node I will label as 1, 2, 3 and 4 like that. And then draw an arrow from AI to AJ. So from one vertex to another vertex there will be an edge if that ordered pair is there in the relation. Okay, so I'll take example. For example, if I say A is my set and it has 4 elements 1, 2, 3, 4 and R is a relation defined on A. So this will be a subset of A cross A. I told in the beginning, no, if R is a relation from A to B, that means R will be a subset of A cross B. But if R is a relation on A, that means R will be a subset of A cross A. So now this set is given and relation is also given. Now the next step is we have to draw the digraph. So digraph means how many nodes are going to come. That is straightforward based on the number of elements. So here I have 4 elements. So 4 nodes are going to come. So 1, 2, 3, 4. Like this I will be drawing 4 nodes. So in circle we will write the numbering. Means this node is node number 1, then 2, 3 and 4. And this I can draw in any way, means I have drawn 1 here and 2 here. I can draw like this also, 1 here, 2 and then 3, 4. So that position of the nodes does not matter. Now I have drawn the nodes. Now how I am going to draw the edges? Edges are nothing but which connects to vertices. So here based on the ordered pair, means 1, 1. 1, 1 means there will be an edge from 1 to 1. 1, 3 means there will be an edge from 1 to 3. 2, 1 means there will be an edge from vertex 2 to vertex 1. 2, 3 there will be an edge from 2 to 3. 3, 2 there will be an edge from vertex 3 to vertex 2. 4, 3 means there will be an edge from vertex 4 to vertex 3 like that. So see, same way 1, 1 we had an ordered pair 1, 1. So 1 to 1 we have to draw an edge. So this is not, if there is an edge from that particular vertex, means if it originates from this vertex and terminate also at this vertex, it is called as self loop. And see, we are telling it's a digraph. So digraph is nothing but we call it directed graph. So that means we have to draw the direction also. Why directed graph? Because ordered pair we say no order matters. If I say 1, 2, so 1, 2 means there is an edge from node number 1 to 2. If I say ordered pair 2, 1, that means there is an edge from node number 2 to node number 1. So that's why it's we always draw a directed graph, means the with direction I have to draw. Okay, now 1 to 3 was there, so 1 to 3 we have to draw an edge, and then 2 to 1 was there was an edge, 2 to 3 there was an edge, and 3 to 2 there was an edge, and 4 to 3 there was an edge. Okay, so like this we will draw the digraph. So now if suppose digraph is given, I have to write the relation in terms of ordered pair. I can write, because this 1 1 is there, so I am going to write 1 1 ordered pair. 2 1 I can write, then 2 3 I can write, 3 2 I can write, 1 3 I can write, and 4 3. So based on the edges I can write the ordered pair with order. So here if I have ordered pair representation, I can write the corresponding matrix and digraph representation. If I have digraph, I can write the corresponding ordered pair and matrix representation. So these are the 3 different types of representation of the relation. Now in directed graph, one more concept we have, degree of a vertex. So when we talk about graph, so we have vertices and edges. So we count the degree of the vertex. So it's a directed graph. So here we have in degree and out degree. So when in degree, what is in degree? The total number of incoming edges for that particular vertex. So see, here I have 4 vertices. So here I am going to write all the 4 vertices, 1, 2, 3, 4. And then these 2 columns are for in degree and out degree. So in degree means the total number of incoming edges to that vertex. Incoming edges means the number of edges coming towards that vertex. If the direction of the arrow is towards that vertex, that will be considered as incoming edge. So here on the vertex number 1, this edge is coming towards it. So in degree is 1. And see, whenever we have self loop will be considered while counting the in degree as well as while counting the out degree. Always remember that. Why like that? Because see, if we say any edge, every edge will have 2 endpoints. See, it is originating from 1 and it is terminating at 3. Based on the direction of the arrow, we will say. See, from 4 it is originating and terminating at 3. This edge, if I say from 2 it is originating and terminating at 3. If I say this edge, it is originating at 3 and terminating at 2. So every edge will have 2 endpoints. One is initial vertex and another one is terminating vertex. But here in self loop, since both my for this edge, both the vertices are same, so that's why this will be considered as incoming as well as outgoing edge. So that's why when I consider a degree of 1, so since on 1 I have a self loop, so this edge will be considered once while counting the in degree. So here how many edges I have incoming edges on 1? This is 1 incoming edges, this is 1 outgoing edges. And this self loop, once I will consider for counting in degree, once I will consider for counting out degree. So that's why for 1 in degree is 2, out degree is 2. Now for 2, how many incoming edges? How many arrows are coming towards 2? Only 1. So in degree is 1. How many are going, edges are going away from 2? So this edge and this edge. So out degree is 2. Now for 3, how many incoming edges? These two edges, the direction of the arrow is towards 3. So 2, and this also it is towards 3. So degrees, in degree is 3, and out degree only 1 outgoing edge from 3. So this is 1. 4, there is no incoming edges on 4. So in degree is 0. Out degree only 1 edge is going from 4. So out degree is 1. So sometimes one simple matrix, some ordered pair representation of the relation would be given, and you have to find the digraph representation and you have to find the in degree and out degree. Some simple question can be asked. So this is all about representation, different representation of the relation. Now next quickly we will see this problem. So here we have 2 sets A and B. So A has 4 elements 1, 2, 3, 4. B has 5 elements 1, 4, 6, 8 and 9. And R is a relation from A to B. Defined by ARB means A is related to B if B is equal to A square. Okay, so this is the relation, means I have to see, now I am saying R is this R such that A tends to B is nothing but this is another way of representing that there is a relation R from set A to B. So instead of writing like this, there is a relation from set A to B. I can represent this way also. So this means R is a relation from set A to set B. So that means R will be what? A subset of A cross B. Now that relation, how the elements will be related, that is defined here. So I have to write all those ordered pair in the relation where this condition is satisfied. A or B if B is equal to A square. Okay. So here in R, what all elements I will write? See, A cross B means what? 1 to 1, 1 to 4, 1 to 6, 1 to 8, 1 to 9, and 2 to 1, 2 to 4, 2 to 6, 2 to 8, 2 to 9. Then 3 to 1, 3 to 4, 3 to 6, 3 to 8, 3 to 9, 4 to 1, 4 to 4, 4 to 6, 4 to 8, 4 to 9. All those will come in A cross B. So each ordered pair, first element will be from the set A, second element will be from the set B. But here, because we have to write only those ordered pair which satisfy this condition, B is equal to A square. So can I write 1, 1? Yes, 1, 1 if I am writing. So this first element is nothing but A, second element is nothing but B. So B square means if I take square of 1, I am going to get 1 only. So the condition is satisfied. Can I take 1, 4? No. 1, 4 if I take, 4 square is what? 16. That is not equal to 1. So I cannot take. So only these ordered pairs are going to come. So I have to check one by one which ordered pair is satisfying this condition. Only those ordered pair I have to include for the relation. So 2, 4, 4 square, B is equal to A square. Okay. So B is equal to A square. So B is what? 4. And A square is what? 4. So 4 is equal to 4. Here 3 square is 9 is equal to 9. So these ordered pairs are satisfying the condition, so that will be included. Rest other ordered pair won't satisfy, so we need not include that. So this is the relation. Okay. Now the set was given, the condition was given, and we had to write the relation. First part is complete. Now we have to tell the domain and range. So domain, I told, from each ordered pair I am going to pick the first element, that will be domain, and from each ordered pair I am going to pick the second element, that will be my range. So 1, 2 and 3 are the first element of each ordered pair, so that will be domain, and range is the second element. So 1, 4 and 9 are the second elements, so that will be range. Now for the same thing, if I have to, for the same relation, if I have to represent it in matrix form, how will I do? So see, matrix form, here A has 4 elements, that means 4 rows are going to come. B has 5 elements, so 5 columns are going to come. Now this is nothing but 1, 2, 3, 4. This represent 1, 4, 6, 8 and 9. So now 1 to 1 is there, so only 1 to 1 I have to put 1. Rest everything I have to put 0. Now 2 to 4 means 2 to 4. Second element represent 4. So 2 to 4 is 1. So I have to put 1 here. Then 3 to 9. So 3 to 9 I have to put 1 here. Then this whole this last row will be all zeros, because anything that starts with 4 is not there. So based on the ordered pair here in the relation, I have to write the matrix. So this is the matrix representation. So same way, if I have matrix representation, I can write the relation in terms of ordered pair. If I have ordered pair, I can write the matrix representation. Okay. So this is about relation basics, what is relation, and different ways of representing the relation. And if any two sets are given and the relation is also given, how to write the set R in terms of ordered pair, how to write the relation R in terms of matrix and in digraph, how to calculate in degree and out degree, those things. Now the next topic is, it is very important, properties of relation. So properties of relation, here first property of relation is reflexive. So what is reflexive property? See, these conditions you have to remember. Reflexive property, it says if R is a reflexive, means any relation, if I say it's a reflexive relation, so that means if AA belongs to R, for each A belongs to capital A. What does it mean? I am saying R is a relation on A. That means R is what? A subset of A cross A. Now I am saying we should have AA belongs to R for each A belongs to A. So what does it mean? If I say, for example, if I say A is equal to 1, 2, 3 and R is a relation on A, that means R is a subset of A cross A. Now A cross A is what? 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Okay, like that. Now, but R and this R is given. Now R is also given. Now we have to determine whether it is reflexive or not. So reflexive, we are not bothered about any ordered pair. We have to just check this AA should belong to R for each A belongs to A. For each A belongs to A means what? Where small a is what? The element of this set A. So A is what? 1, 2 and 3. Okay, so for each 1, 2 and 3, I should have 1, 1 pair, I should have 2, 2 pair and I should have 3, 3 pair. AA means that only. That element 1, 1, 2, 2 and 3, 3 should be present in the relation. If it is present for each element of A, then we will say that the relation is a reflexive, otherwise it is non-reflexive relation. So for this particular example, I am not bothered about 1, 2 and 3, 2. I have to just check whether 1, 1, 2, 2 and 3, 3 is present. If 1, 1, 2, 2 and 3, 3 is present, I will say that it is reflexive. Now suppose for this particular example, if I say A is equal to 1, 2, 3. Now R is a relation that is given 1, 1, 2, 1, 3, 2 and 3, 3. Now we have to determine whether it is reflexive or non-reflexive. So now what I have to check? I have to check 1, 1, 2, 2 and 3, 3 should be present. If any one of these is not present, I will say it is non-reflexive. Why? Because this AA belongs to R for each A belongs to capital A. So for each A means even if for one single element also this condition is not satisfied, I will say that it is non-reflexive. So here 1, 1 is there, 2, 2 is not present, 3, 3 is there. So 2, 2 does not belongs to R. For one pair it is not true. We will say that R is not reflexive. Okay, so this is first property of the relation. Now the second property is irreflexive. What is irreflexive? Irreflexive property. Here we say that a relation R on set A is irreflexive if AA does not belong to R for every A belongs to capital A. So that means none of this AA should be there in the relation. If any one AA is also there, it will be irreflexive. Okay. So now suppose if I say R is a relation and set is same A1, 2, 3 and it is 1, 2, 2, 1, 3, 2, 3, 1. So see here, none of 1, 1, 2, 2 and 3, 3 should be present in the relation. Then I will say that it is irreflexive. So here 1, 1, 2, 2, 3, 3, none of them are present. So it is irreflexive. So don't get confused. Reflexive means for each small a belongs to capital A, AA should be present in the relation. Whereas irreflexive is for none of the AA should belong to R. Okay, that is irreflexive. So if the relation is not non-reflexive, it is not irreflexive. It is different. Both are different. In non-reflexive means even if for one element it does not belong, we will say it is non-reflexive. But irreflexive means none of them should belong. Okay. Now suppose I take this example. R is a relation on A where A is 1, 2, 3 and this is my relation R 1, 1, 1, 2, 2, 1, 3, 2 and 3, 1. So this relation is not irreflexive. Why not irreflexive? Because 1, 1 is there. None of this AA should be there. So 1, 1 is present. So it is not irreflexive and it is not reflexive also. Why? Because 1, 1 is there but 2, 2 and 3, 3 is not there. Okay. So that is the difference between reflexive and irreflexive. Now the next is symmetric relation. Symmetric means we are saying when A is related to B, then B should also be related to A. Means if A or B is there, B or A should also be there. Okay. So that means if I say 1, 1 is there. So 1, 1 means the reverse of 1, 1 is 1, 1 only. Okay. So anyway, when it is set, I am not going to write the repeated elements. Now 1, 2 is there. So if 1, 2 is there, then only I will check for 2, 1. Then 2, 1 should also be present. 3, 2 is there, 2, 3 should also be present. For any other pair, I am not bothered. I am seeing if A or B is there, AB belongs to R, then BA should also belong to R for that pair. Okay, that is symmetric relation. Now if I say this relation, see 1 2 is there, so I should check for 2 1, it is there. 3 2 is there, then 2 3 is there. Okay, now 1 3 is there, so 3 1 should also be present. Correct? So 3 1 is not present. So for every A belongs to A and B belongs to A. Okay, if A or B is there, B or A should also be there. So for 1 3 3 1 is not present, so we will say that it is not a symmetric relation, but this one was symmetric. Now what is asymmetric? Asymmetric says a relation is asymmetric whenever A or B, then B or A should not be there. Means if AB pair is there, BA should not be there. Whereas symmetric says whenever I have AB, I should check for BA also. But asymmetric says if AB is there, BA should not be there. Then it is asymmetric. Okay. So here if I say this one, 1 2 is there, that means if I am checking for asymmetric relation, 2 1 should not be there. 1 3 is there, 3 1 should not be there. 3 2 is there, 2 3 should not be there. So it is not there, so it is asymmetric. Okay. Now here if I say this relation 1 2 1 3 3 2 and 1 1. So 1 1 is there. Okay. So reverse of 1 1 is 1 1 only. 1 2 is there, so 2 1 should be there. 1 3 is there, so 3 1 should be there. 3 2 is there, so 2 3 should be there. So that is not there, so we will say that it is not a symmetric relation. Then the next one is antisymmetric. So antisymmetric says if A or B and B are A, means when both are there, when AB is there and BA is there, when both the condition are true, then only we will see A should be equal to B. Okay. When suppose AB is there, BA is not there, I won't go for checking this condition A is equal to B. If AB and BA both are there, then only I will check A is equal to B or not. Okay. So here in this relation, see 1 1 is there. So reverse of 1 1 is what? Means if it is AB, so what is BA? 1 1 only. So that means it is present. So now 1 1, AB is 1 1, BA is also 1 1. So A is equal to B, 1 is equal to 1. That is correct. Now 1 2 is there. Now we will check whether 2 1 is there. So 2 1 is not there. So we will not check for this condition only, because it says when this and this. So when there is and clause, that means both the condition should be true. Then only I will check this then condition. Okay. So 1 2 is there, but 2 1 is not there. So I will not check for A is equal to B. So I need not worry. 3 2 is there, 2 3 is not there. So I will not check for A is equal to B. So this one 1 1 ordered pair, AB and BA both are there. So A is equal to B condition is satisfied. So this is antisymmetric relation. Now if I say this one, okay, this example, 1 2 is there, means AB is there. So what is BA? 2 1. 2 1 is also there. Now A is equal to B, 1 is equal to 2. That is not possible. So we will say that it is not a antisymmetric relation. Okay. Now next is transitive property. So transitive says if AB is there and BC is there, then AC should also be there. So this also when both the condition AB and BC both are there, then only I will check for AC. Suppose only AB is there or only BC is there, I cannot check for AC. So this also and clause is here. When A are B and B are C, that means AB and BC is there. Now I should check for AC. Okay. So say don't get confused. Here it is written A R B. I told in the beginning A R B or AB ordered pair. Both are same. So now here in this we will see 1 1 is there, that is AB. What is BA? What is BC? 1 1 is this. So BC is 1 3. See, this is A, this is B. So this is C. So this is AB. This 1 3 is BC. So AC is what? 1 3. 1 3 is present. Now 1 1 is there, and now we'll check another pair. 1 3 is there. Anything that starts with 3. So 1 3 and 3 3 is there. So 1 3 should be there. That is present. Now 2 3 is there. 3 3 is there. So 2 3 should be there. That is there. 3 1 is there and 1 1. So this is A. This is B. This is B. This is C. So 3 1 and 1 1. So sorry, 2 1 and 1 1. So 2 1 should be there. It is there. Similarly 3 1 and 1 1. So 3 1 should be there. That is there. Now 3 3 and 3 1 is there, so 3 3 should be there, that is also there. So it is satisfying all the property, so we can say that it is transitive. So see, basically in transitive, if I am checking for each ordered pair, you have to start from the beginning. If I am saying this is A, this is B, so I have to find BC, right? So BC means anything that start with 1, that pair I have to find. If that pair exists, then I will check for AC. If that pair does not exist, I will not check for AC also. So this is all about properties of relation. So next class I will discuss the next topic of relation. Okay, thank you.